You guys, can we see that okay?
Yeah.
Yes, we can.
Okay. So I would like to welcome you all to our first technical lunch and learn. I apologize if there's any logistical things. It's our first, so we're still kind of getting the hang of it, but really excited to welcome everybody from Rise Design Automation. Today, the speakers are going to be myself, Ellie Burns-Brookins, and Mike Fingeroff and Alan Klink, and I will introduce them in all their glory as we get ready to turn that over to them. Okay, so today's agenda, this is really the introductory section. So I'm going to give a little bit of an introduction myself, which is just a few slides, bear with me on the marketing piece, kind of to give you kind of a little bit of a foundation. Then we'll turn it over to Mike for HLS 101, and really we're focused from an RTL designer's viewpoint. So I know we've got verification folks in here, we've got design folks in here, we got lots of different folks. What we're really going to do is take a little deeper dive into looking at this from the RTL designer's viewpoint. Have Mike walk through the design and then go into a live demonstration. This is going to be brave, tool running live now with the tools and the AI advisor with Alan, and then show you some design space exploration on a pretty big design. So that's what we're going to do today. And I really want to try to, like I said, encourage you to ask questions, encourage you to interact. And then, but I do want to try to get through most of the material in this 1 hour. Be respectful of your time, but we will hang around later and answer Q&A. Okay, so let me go ahead and kick it off. If you guys haven't seen this already, the semiconductor industry is growing. Like I've been in this industry for over 3 decades now, and it's been a long time since I've seen this kind of growth. I mean, it's projected to be 1.1 trillion by 2030, and as you guys probably all of you know, driven by AI and ML, communication, 5G, Internet of all things. But the exciting part about this, or maybe not so exciting, CPUs are not keeping up, right? You are needing custom acceleration. All of those applications tend to be either very power and performance sensitive or really need their own hardware. So we're seeing a huge demand in new designs and new silicon. At the same time, we are seeing that, and have been seeing for years as I've been in this industry, that the RTL design methodologies, they're really good and they're known and they're understood, but they're not quite keeping up, right? We're seeing critical time to market things, the hardware design time is still growing, verification time is still growing. You're often unable to, this is actually one of the biggest ones we've seen lately for companies big and small, is they're unable to hire the number of RTL engineers and verification engineers in order to meet that time to market. So some change has been needed for a while, and we're starting to really excitingly see more companies focused on how are they going to deal with this productivity? How are they going to do the next generation? And we see, I mean, really as an industry, we need to change the level of abstraction across the industry to significantly improve this to take us into the next generation. We have seen, and I have seen, I mean, some of these come from my efforts over the years, raising abstraction has already proven to be very valuable, right? You can start verification much earlier, your design is faster, your architectural and exploration, you can combine architecture plus algorithm and verification and do all that much quicker. Your RTL debug time is reduced. And it's proven. I mean, folks like NVIDIA, ST, Google, Qualcomm, all of these have been able to raise the design abstraction for projects and have documented how valuable it's been for them. However, so if it's so valuable and you cut the project time, you may wonder, well, why has it not been adopted at scale? And kind of trying to sum up the reasons. I mean, there's lots of different reasons why we haven't seen just broad adoption, but I'd say they kind of fall into 3 different camps as we've analyzed this. A little bit about language barrier. Not everyone is able to move from a traditional HDL language into a C-based language. It throws them curves in adoption and learning and things like that. Lots of different things around that. For RTL designers, the unpredictability of time to achieve the quality of results, because the design is all about meeting power, performance, latency, and functionality of the design. And sometimes that's been unpredictable or unknown by teams, and they're not willing to take that risk. And there's been challenges in there. And then the other ones fall under the kind of the camp of verification. It hasn't been in the early days really productized as a first class citizen. And so there's been kind of a lack of trust in whether it was going to be predictable for verification flow. Lots of different things, but I'd say kind of generally in those camps. And I wanted to highlight a little bit more, just kind of looking at this. We do see that the current solutions, just to summarize, as you try to bring together the algorithm, the system people, the software people, the verification team, you're asking the verification team who's used to Verilog, VHDL, and used to their simulators and their synthesis tools to make basically two leaps. One, the leap in abstraction, which we can help understand, but the second one is also a leap in language. And many can make that, but many cannot. And so as we look to the solution that we needed to provide, we needed to really think hard about how we can ease the barriers of adoption, still get that productivity, still bring those two teams together and up and enable that. So one of the things that we've focused on is trying to really bridge that gap from system to silicon. But I think probably more importantly, when you do that, you can't just, like creating a model enables value for the software person, but makes it harder for the system person. You need to enable value for everyone. And so as we look at this, we have unified with basically multi-language and multi-abstraction support in the same environment. So you can choose the language that you need, choose the language that you want, and gradually raise the abstraction or gradually switch and basically mix and match. So the system architects can basically do high-level models that enables them to do performance analysis, identify system bottlenecks. The RTL designer could take that model, refine it, gradually add detail to meet his important PPA goals. Verification engineer start much earlier, and we have some auto-generated transactors and adapters that come out of the synthesis process that Mike will talk about. And of course, the software engineer needs to be able to test the software on an early platform as early as possible, even as early as the architectural models. So again, being able to bring all those people together with a unifying model. So what we do, we accelerate the process of hardware design and verification, and really using currently 3 different languages. You choose which one you want, either SystemVerilog, C++, or SystemC, or any combination of those. And Mike will show you the details of that. The user develops code and functionality in what we call untimed or loosely timed SystemVerilog or C++. And these terms, I'm not sure if they have a fixed definition across the industry. Mike will show you a lot more about what this means. Untimed C++ and SystemC have been out there for a while, introducing what that looks like in SystemVerilog, because obviously you know SystemVerilog for verification and transactions and other things like that, but you probably haven't seen it for untimed and loosely timed for high-level design. The tool then adds all the implementation detail, finding the architecture, memory. Again, we'll go through that standard kind of high-level design techniques, and Mike will show you. And the tool delivers quality, synthesizable RTL with superior Q of R. That's extremely important. Obviously, if you lose the Q of R, you can't use this as a production level tool. So Q of R reports, and then additionally, the verification components that allow you to plug and play. Okay, so that's really what we're doing and what we're going to focus on today in this introductory session. We're delivering a unique solution and value in that perspective, and that the synthesis is easily 10x to 100x faster. And so that really, with that predictable Q of R, enables a lot more exploration, looking at different performance, timing, and area power trade-offs, because as these designs are getting more and more complex, oftentimes RTL teams have to pick one way to do it. They don't get time to explore what could possibly be a better implementation. 30x to 1000x faster verification. I know that's a really big range with the verification components that plug and play into the test bench, block to system verification. A lot of that I'll talk a little bit more about, but it's about the level of abstraction that you decide to choose. The higher level of abstraction that you choose, the faster that it goes because you just remove events from your favorite simulator. Integrated in modern VS Code. We're in a place now where all of this infrastructure is possible, and we've reused a lot of that. So the analyzer makes it easy to understand, from the high level design all the way down until the lowest bit of RTL, you can trace all of that transformation and what's happened. And then AI Advisor, which Alan will talk a lot more to give you, we're in the era of generative AI and letting all of this in a natural language model be able to help you with that expertise. And then built on an open modular foundation, which is one of the keys to us being able to innovate and to scale very quickly. So a couple more really quick, just introduction to the of kind of the architecture and why we're able to do. One of our key mantras has been innovation at scale. And really what that means is we need to be able to not only use what's out there, which is everyone else innovating, but also to be able to have something that's very modular so we can quickly add new components to it. So it's very modular, very separated, where you can see here we've got language support of, like I said, SystemC, C++, and now SystemVerilog, and can add things like domain-specific languages and other into that front end. We do several high-level optimizations, so we stay close to the code, can understand that quickly. And then structural optimizations, we've been partnering with Google and Google XLS Core, which gives us the backend kinds of silicon-proven optimizations that HLS is known for. So an important part of this is we have an open IR, which has been really interesting because this enables us and others to look at kind of debug and analysis, verification. It enables us to understand each of the levels of transformation so that the debug is very open and understandable about how you got from the high level design down into the RTL. And then on top of that, and Alan will show a lot more about this, is AI is just taken by us in the programming area, but a specialist AI for high level design. So code completion, generation, expert advice, all powered by powerful large language models. Again, giving us full analysis and verification visibility. So before I turn it over to Mike, which I'll do quickly, and you guys can be rid of all the marketing pieces of this, I just do want to one more time explain a little bit about this mixed language and mixed verification, understanding the speed and the abstraction trade-off, right? So first of all, in the RISE environment, you can choose any of those languages. Today, we're going to show you a mixture of C++, SystemVerilog, and SystemC, so you can see some code snippets. But really the fastest is untimed C++, traditionally, right? That's where you get, I have 1000x, but I see more than that in other customers, right? So you've got, it's untimed, it's C++, the simulator is the compiler. Next down, you get more threaded capabilities, which we can also do in C++, but untimed SystemVerilog. So using your favorite SystemVerilog simulator, but you don't have all of those individual cycle by cycle timing, and so it speeds up the simulator dramatically. Loosely timed, which is it's kind of been a common definition in some circles, but Mike will show you a little bit more about what exactly we mean by that. And then RTL you're familiar with. And then we could easily mix and match all of that, plus generation of the verification components, right? So that we give you all the transactors and adapters to go from behavioral to RTL and RTL to behavioral in all of those languages so that you can come up with your own methodology for verification and have all that auto-generated. Okay, and then of course we support all of the standard high-level design libraries, right? So AC data types, AC math, these are all silicon proven and have been for years with all of the folks out there that are using them, and MatchLib, which is again commonly used hardware components, which you may not have heard of so much, but it's founded by NVIDIA Labs and NVIDIA. So use them, and you'll see some pretty big designs today that are using that, and fully tested and verified in both a C++ flow and in a SystemVerilog flow. So you can choose those data types in either flow. Okay, hopefully I didn't talk too fast and there were some questions in there. I am going to introduce our speakers and then turn it over to them. So first we're going to have Mike Fingeroff, who's our Chief of High-Level Design. Over 2 decades of experience in hardware design automation. Mike's been specializing in high-level synthesis for a long time, focusing on machine learning and early performance modeling using SystemVerilog, SystemC, and MatchLib, and he's the author of the High-Level Synthesis Blue Book. And after Mike, we're going to have Alan Klink, who of RDA and a technology leader with expertise in high-level design, AI and ML frameworks for verification, and he's driven multiple innovations in verification and low-power technologies, helping teams to advance their efficiency and performance. So Mike, I am going to turn it over to you.
All right, thank you very much, Ellie. Okay, well, once again, welcome everyone. Ellie, can we see my screen?
Yes. I can.
Okay, so this is going to be a review for people that are already familiar with HLS, but essentially I'm going to talk about what is HLS really doing, and it's really part of high-level design. And then we'll look at some code examples to see what does the language look like, what can the tool do with those descriptions, and then we'll do a live demo. And then Alan is going to do some really amazing stuff that you'll get to see, some AI magic, and then we'll finish up with a bigger design. So what does high-level synthesis do? So it converts untimed or loosely timed SystemVerilog C++ or SystemC descriptions in RTL, and we'll talk about what do we mean by those terms. One of the big things is it does automatic timing of the design. So it inserts pipeline registers to meet your worst case critical paths based on clock frequency and technology. It adds data flow control on the interfaces. So we'll look at the types of interfaces that simplify design and integration because you don't have to worry about doing low-level synchronization of various processes and modules. It enables exploration of parallelism, so you can use design constraints to add parallelism into design to increase performance. And it infers memories from arrays, so you don't have to manually think about how do I hook up an on-chip memory, what is the timing, what are the control signals. That's pretty much done push button. And there's lots of other things, but these are kind of the things I'm going to focus on for this discussion. So we've heard these terms, untimed versus loosely timed. I'm going to throw in fully timed, and let's just quickly say, what are they? So fully timed is what designers know today. It's RTL design, and it means that the language is completely cycle accurate. You're describing the cycle-by-cycle behavior. You're manually inserting registers for storage and registers for pipelining to meet timing. It's very detailed, but it requires a lot of effort. And ultimately, also for very complex designs, it's slow in simulation. Untimed language allows you to model the functionality without describing any of those low-level details that I just talked about. So C++ is an example of an untimed language. There's no clocks, there's no resets, there's no events, and so it's not cycle accurate. And so this language tends to be better for data path-centric designs, which can include control, but because you don't describe clocks and resets, it's better focused on data path, though we're looking in the future at being able to expand the capabilities of untimed C++. It's the fastest simulation. As Ellie mentioned, it's somewhere in the order of 1,000x faster than RTL. And then loosely timed is giving you approximate timing. It may not be latency accurate, but it's throughput accurate. And it provides you the ability to do early validation and system level analysis. And this language is a little bit broader in that it allows you to do both data path and more control-centric designs. And gives you kind of a balance of accuracy versus simulation speed. So it may not simulate quite as fast as untimed C, but still much faster than RTL. So let's first talk about what is the challenge of doing fully timed design, so doing RTL design. So in RTL design, one of the benefits is you can describe exactly what you want at a very detailed low level. But because of this, you have more code overhead. So you have more lines of code, which means it's harder to debug and it's slower to simulate. The other thing, and this example here may not run through all RTL simulators, but I do know that this works, is that for this description, when you have loops in the design, whether or not they're behavioral loops or like generate loops and generate statements, loops are always implemented in parallel. So I have no control over the microarchitecture of this implementation. It's pretty much fixed. I'm going to get a parallel multiply add tree. And in this example, I'm going to produce one Mac output every clock cycle. Um, if you look at the generated RTL, you immediately see one of the limitations of this type of design description is that the timing is fixed. So I end up with a multiply add tree in this particular design description. And as I increase the clock, at some point, I'm going to start to fail timing because I'm going to have negative slack. I'm not going to be able to squeeze this multiply add tree within a clock period, and I'm going to fail timing. So that's undesirable. So again, this is somewhat one of the possible limitations of RTL design. So the advantages of untimed design is it's way less code. So you've got on average, 10x less code, so fewer lines of code, which means it's easier to debug. Whether or not we're talking untimed C++ or untimed SystemVerilog, it simulates much faster. So anywhere from 100x to 1000x faster than RTL simulation. And with these languages and a high-level synthesis tool, you now have control over parallelism, performance, area, and power. You get to turn the knobs in the tool and apply constraints in order to achieve your design goals. Now, one of the limitations here also is because it's untimed, as I mentioned before, you don't have explicit control over the clock and the reset, and this somewhat limits how detailed you can model, especially for very control-centric designs. So if you look on the code on the right here, you can see that I have examples of untimed C++ and untimed SystemVerilog, and they look very similar. I have basically a design. It's doing a multiply accumulate. It's got a loop with 8 iterations, and there's no clocks, there's no resets, there's no wait until pause edge clock. And this is going to give you the fastest simulation speed and the most flexible coding style. But as I mentioned, there may be reasons why we want to add time in. And when you simulate this, we get one Mac is produced every function call or so there's no concept of time in this case. For loosely timed design, we're going to add in the clock and the reset. So again, it's much less code than RTL, so it's easier to debug. There's a little bit of overhead for describing clocks and resets. Because I can define clocks and resets, I can do more control-centric designs because now I can actually code data or operations into the reset action of the design. It still simulates much faster than RTL, anywhere from 30x to 300x faster. And it's good for early performance analysis. So I have the ability to basically model kind of the ultimate hardware behavior at a much higher level and get timing information in terms of throughput. As I mentioned, maybe latency is not quite as accurate. And so if you look at the two description here, I've got loosely timed SystemVerilog and loosely timed SystemC that I have a clock sensitivity here, so always at pause edge clock. And then I've got my reset action where I'm clearing some of my local variables. And then I've got this multiply accumulate loop. Well, what we're going to see is that with high-level synthesis, I get to decide how fast should this multiply accumulate loop get implemented in hardware. And so it could have anywhere from being implemented with one multiplier all the way up to 8 multipliers in parallel. So I get to tune the performance using a design constraint, and the tool takes care of all the low-level details. And pretty much, these descriptions are the same. Here's my SystemVerilog. Here's my SystemC where I'm defining some ports. I've left out the constructor, but there's a clock sensitivity list described in here. And the code pretty much is the same in here. So even though if I simulated this just standalone, I'm getting 1 Mac per clock cycle in simulation, I have the ability to change that behavior when I actually implement the RTL. And I also can annotate additional information into the simulation. So why use high-level design tools? So the first is time enclosure is automatic. That's a really big deal because as you have IP that's been developed for a certain process and technology, retargeting it may be difficult. So you don't have those concerns. The pipeline data flow control is built in using the interfaces, and we'll see all this. So again, it simplifies the design process. You get to explore parallelism as a design constraint. Adding memories into your design is simple. Getting to verify the behavior of the generated RTL is also a pretty push button, as we'll see. And then ultimately, these designs are going to be reusable across technology and clock frequency. So the first thing is, how does HLS automatically close timing? So high-level synthesis is going to insert pipeline registers to meet your clock frequency constraint based on the technology that you're targeting. So it understands the speed of the various operations, the multipliers, the adders, AND gates, and OR gates. And this is what's known as scheduling. And so the beauty of HLS is I could even take that original RTL example that we had that was building a parallel multiply add tree, and I can run it through high-level synthesis with a fast clock. And for a specific technology, all of a sudden, the tool is going to start to add in pipeline registers in order to make sure that the worst case reg-to-reg path is going to satisfy that clock frequency constraint. So it's very powerful because now I have a technology, a somewhat technology independent solution. So if you look at that last example, though, it was just data comes in, data comes out at some latency later. And so how do you know when to provide data? How do you know when data is going to be available? And so you can use streaming channel interfaces that are provided as a library to basically give you transparent data flow control. And these interfaces are going to be synthesized using a data ready valid protocol. When you synthesize using these streaming interfaces, you simply define them on your module interfaces and you specify the data type. So here you can see I've got some 8-bit data that's being packed into an array, and I'm producing a 19-bit output. And this is going to then automatically create a data path FSM to manage the IO and the pipeline control. It allows users to focus on the high-level architecture. And the data transfer is very simple in the source. It's transaction level. So you can see here that I'm simply doing reads and writes within my code. And these are going to translate to data read valid. And if data is not available to be read, it's going to stall the pipeline. And likewise on the output, I'm going to do writes, and that's also going to stall the pipeline, or it's going to block if the write can't complete. And so high-level synthesis is going to take care of all those low-level details. You simply focus on the functionality to get your architecture right and meet your performance requirements. Parallelism is added as a design constraint. So you can use what's called loop unrolling to say how much of a loop should be implemented in parallel. And so here you can see I've added in SystemVerilog, and from this point forward, I'm going to focus on SystemVerilog. That will be the demo, and we'll circle back in future webinars to dig more into C++ and SystemC. But here I'm using a Verilog attribute on this loop that says unroll it 2 times. So what I'm saying is I want you to implement the loop body 2 times in parallel in order to increase performance. And now when I synthesize this, what I'm going to get is a scheduled data path and an FSM that's going to control that data path. And so you can see now that by unrolling by 2, I'm going to get 2 parallel multiplications that then feeds a smaller adder tree. So again, it's very easy now to basically work on performance and not worry about the low-level details of achieving those requirements. A couple more items on, what are the bells and whistles of high-level synthesis, and one of them is designing with memories. So when you start to have complex memory architecture, it becomes much more difficult to code your RTL, as well as, there's going to be more debug just to get it right. And so with HLS, we can infer memories from arrays, and that's true for any of the languages we support. And what that means then is when an array is going to be constrained to be a memory, we are going to synthesize on the top level RTL interface the address, data, and control signals that allow you to interface to an on-chip memory, which is going to be either a single port, a dual port, a registered file, and things like that. And so you can see here now in my SystemVerilog design, I have this array and I've added this memory attribute. I can also specify the memory type, whether I want single port or dual port. And now the tool is going to synthesize this where my array accesses within this code are going to translate to memory transactions. So you can see here now I've got address data, read enable, and write enable, and those control signals are going to be toggled based on how these transactions are scheduled within the design. And so again, the beauty here is you focus on functionality, not on the low-level details. And then lastly, how do you verify this? So we're auto-generating RTL. How do you know it's correct? How do you go ahead and verify it? And so typically an RTL designer, they have to sanity check the RTL before they hand it off to the DV team. And so we auto-generate verification adapters as well as transactors that allow the generated RTL to be plugged back in to an RTL test bench. It could be a behavioral test bench. It could also be, cycle accurate RTL. And this also then gives the ability of the verification engineers to basically get early access to the hardware, either via a behavioral interface or a pin level interface. And we're not going to dig into the details for this webinar, but we're going to dive deep in verification for some of the upcoming webinars. So let me do a quick demo, and then I'm going to hand this over to Alan.
You still have plenty of time, Mike.
Yes, I'm just looking at the clock.
Yeah.
Okay, so
Yeah.
I'm going to start simple. And so I like simple when explaining A, what does HLS do? And B, how does the HLS synthesis tool work, as well as how can you do analysis? And so it's just going to be a FIR filter, which fundamentally is a bunch of multiply accumulates, similar to what we saw in the slides. We did not develop a GUI for this design flow, or what we did was we developed an extension for VS Code. So VS Code is a very modern graphical interface. It's an IDE. It has tons of extensions, and so we were leveraging all the work that's been done with VS Code, adding in our analysis extensions, and also being able to take advantage of some of the other extensions. So you'll see here I've got some SystemVerilog. I've got some parameters. So it's a 31 tap filter. I've got 20-bit integer data. We support fixed point as well as in SystemVerilog. We'll show that in a future webinar. And the first thing you see before I've even done any analysis or synthesized the design is I can browse the my SystemVerilog. So we have browsing capabilities that let you go through and simply see the structure of your SystemVerilog. In this example, it has a shift register, which is going to store a history of data. And then we've got a loop that's going to implement the multiply accumulate of the shift against the coefficients. And you can see here, I'm saying I want to do 2 iterations of that loop in parallel. So the first thing I'm going to do is I'm going to synthesize the design. Oops. So RDA Builder is a Python interface that runs all the various runners in the tool and basically runs the synthesis of the design. It's very simple to use and very powerful. So I'm basically specifying my SystemVerilog file, my top level module, and I'm specifying a clock period of 2 nanoseconds, turning on flops on the inputs and outputs and things like that. So let's go ahead and synthesize the design. And the first thing you'll notice is this tool is extremely fast. We don't do a lot of low-level RTL-ish optimizations. We leave that to the RTL synthesis tool. So you blink and it actually synthesized that 31 tap filter. So now let's bring it up in the analyzer and look and see what happened. So the first thing is I enable the RDA analyzer extension. So you'll see now it changes. It shows me the RTL files that were used in the synthesis process, the various scopes in the design, the various high-level instances, as well as also my RTL instances. And we have some verification waveform debug that we'll show when we cover verification in a later webinar. So the first question is, we synthesized the design, what happened? So I can go to the table view, and we provide textual reports also that are interactive within this view for pretty much all the different optimization phases. They're also available as CSV files, so you can post-process as you like. So this is telling me I've got 2 pipeline stages, and it gives me the worst case critical paths for each of the pipeline stages, as well as the total number of flops and some other additional information. It gives me the critical path broken out by pipeline stages. So you can see basically my pipeline stage 0, here is my unsigned multiplier. It gives me the various delays of the ops, and then you can see what's going on for the various pipeline stages. Register reports, summaries of what are the types of operators that were used within the design, bill of materials. And then the last one, I'm not going to go through all of these because I'd like to get to Alan's design space exploration. It gives you a graphical view of the design schedule. And I'll show you, we also have, or sorry, not graphical view, tabular view. We also have graphical views. And the one thing I like about this is as designs get really complex, it's hard to visualize graphically the whole design, because you need to kind of drill in on specific features. And this is very easy to understand. So what it's showing me is how the design has been scheduled over time. These are the various pipeline stages. It shows locations within the pipeline. So these are kind of the data dependencies. It shows where IO is occurring. And then it breaks things down into light and heavy ops. Heavy ops being things like adders. So it's showing me where in the code adds are coming from, as well as also multipliers. So multipliers right here. So it's showing me where the multipliers come from, and then also shows the IO and breaks down various dependencies and things like that. So it's very easy to get an idea about where are all the objects located within the design pipeline that was created. In addition to that, we have various graphical views. There is a post-schedule view that graphically shows what I just was demonstrating in the tabular view. And this is essentially showing how the pipelines have been laid out, what the various ops are within the pipeline. This is kind of an early version of this. I expect it to become a little more sophisticated, but also, like I said, as the designs grow in complexity, it's very hard to sometimes visually look at these things rather than post-process them. It also has CDFG views. So if you have, it'll show you kind of the IOs in your design, where conditions are branching and things like that. Not that interesting on a simple design like this. And then lastly, I'll show you this, and then I'll hand this over to Alan in a second here, is we also synthesize things like display statements for debugging, covers, and asserts into the RTL. So here is my generated RTL. It's got some multipliers in it that it's created and will instantiate for those two multipliers right here. And then we can see that it has generated the display statement, so I can actually look at my RTL and debug it. We have RTL schematics that show you the critical path. This is the schedule IR, so this is very tightly coupled to the IR database. And again, this is why looking at things graphically can be complicated. It's kind of a sea of gates, but you do have the ability also to go in and say, show me just that section of the code. And sure enough, then these are my 2 multipliers from my unrolled loop feeding my mini adder tree and the FSM logic. One last thing I'll show you before I hand this over to Alan is how do we know that this is correct? And so what we have done is we have auto-generated a verification adapter that has the same module declaration as my original behavioral model. And in that, it has transactors that are converting to and from signals. So basically, it's converting from behavioral to RTL and back to behavioral, and it's running the RTL under the hood. So if you look at my test bench here, where I instantiate my behavioral RTL, I can swap that out with the generated RTL, and rerun verification and redo my self-checking that I've implemented in the test bench simply by running VCS. And I can show you basically here that this is my synthesis or my file list for VCS, and I'm just synthesizing the adapter at the end. And if I go ahead and I run VCS, it goes ahead, it synthesizes it, it says the RTL passed. I can bring up the viewer. So it generated an FSDB file, bring up the viewer, load my waveform. And what we see then is roughly that it's requesting data about every 16 clock cycles because it was a 31 tap filter. So it, that takes basically with 2 multipliers at a time, about 16, and then it's producing outputs every 16 clock cycles. And there's lots more I could show you, but I'm going to leave it here for now, and I'm going to hand this off to Alan.
Well, then Alan needs to be ready. Hello. Let's see. Do you see my screen?
We do.
That's exciting. Hello. I'd like to talk about the generative AI aspects. And for us, it means 2 things. It means the RISE.ai advisor, which is really everything you expect from modern integration of generative AI in a design flow. It helps you create code faster, better, help you learn at the same time. Somebody was asking questions about how can I know if my design is optimal or best possible for a synthesis flow or verification flow. You will ask the advisor how to do that. It helps you generate better code by creating code completion. I'm pretty sure all of you are using any variation of a generative AI machinery in other languages. For us, we created a RISE specialized version that is expert in our use case and our tool chain. It means that you can generate code, you can refactor code, you can use it to answer questions about the design and verification. You can use it to ask questions on, is my code optimal for a specific target? It wouldn't do it unless you ask it to do, but you can use it as instead of calling a colleague, maybe you want to use it as a partner to optimize your code against a specific objective. The way that we have set it up is that it comes with a knowledge base that is aware of everything we know in terms of IPs, that, like as Elia talked about, talks about the libraries, the HLS libs, and everything related to that, coding standards, best practices, design patterns, what you should and what you should not do, such that knowledge for high-level design with SystemVerilog, SystemC, and C++ is in one place. What we have also done, and I think this is mind-boggling, and I will show you that shortly. Now, when you have a knowledge about best practices, you have a high-level design, we have connected that to language models, which means that now the machine can ask itself and ask the RISE tooling on how it might go and do something. So you can create, we call them agents, function calling, there's many names, but it's the mechanism where you can use language models to intelligently search and do things that people would otherwise do for finding solutions that otherwise could have been human interactions. You could do that automatically. We architected the advisors with all the experience we have for different companies has different rules for how to deploy generative AI. Some people are very trustworthy for cloud providers like Amazon, Microsoft, Google. Some people have concerns. Some people have concerns about which language models can create what and who owns that IP. We do not create a language model. We create a knowledge base that is connecting to many, many kinds of language models, because you have different language models that are specialized in not so much on tell me the weather in Paris or why is the sky blue, but more about how can I do something. And that specializations comes with specialized language models, and we connect all of that together with the advisor. I will show you this shortly. As Mike outlined, one of the benefits with high-level design is when you are in an on-time world, you have a tremendous amount of freedom to change the shape, change the implementation of the design. So unlike what we are used to in RTL design flows, where we have to go back and spend a tremendous amount of manual labor to reschedule a time, a design, we can do that very easily in a high-level design flow. That becomes particularly interesting when you are working in a design space exploration mode. So early on, when you would like to know, get an early indication of power, early indication of throughput, early indications of latencies. Traditionally, what people will do is to do a brute force sweeping of all the input parameters, such as log pipeline stages, unrolling, and etc., as Mike talked about. But that's very compute intensive. As Mike showed you, with runtime in seconds and not hours or days, you can truly do a lot of iterations and explore very cleverly. The clever part for us means a language model is trying to predict, based on what you have seen, what might be the next point I should go and search for. And this loop is therefore searching like a gradient descent, finding the optimal implementation based on what your objective might be. But enough about me talking. I think I should just show you this and it becomes very clear. I hope it will be very clear. So if you still see my screen, let me go through a very simplistic case. We start with a day in the life on just a combinatorial piece of Verilog. This code is very simple. And it's not because we love simple designs, but simple designs are extremely good for showing the concepts. I hope I can show you the real meaty examples, but we got to get the concept right. Otherwise, it's just a sea of code and it doesn't make any sense. So in this example, as Mike said, we could call the advisor, and the advisor is a chat interface. It comes with the predefined prompts, and I can call the prompt in two ways. Here's the predefined prompts that I use. You can build your own. It's just a configuration settings. So you could say, well, for this example, could you just run me similar to what Mike showed? And you can then, it will build your command line argument, and then you can copy and paste that into a prompt and it will work. You could also use the tool calling. I'm building a story here where tool calling will say, well, what does you want to do? Well, in this example, I would like to use a specific technology and target a specific clock. It will then figure out what on earth that means. It will call the tool from the language model, call the tool. Think about that. Call the tool from the language model, and you will then see log files, what it will running, the RTL similar, what we'll do, and key statistics. And that's wonderful. But you could also use language models to be clever about verification. It can help with finding boundary conditions. It can help finding binary conditions and create verification aid. As Mike said, it will be synthesized into the RTL, so you could use it both for simulation or for emulators, whatever hardware assistant verification you might have. What we're also finding is that language models are very useful for transformation of code, so refactoring. So what if I want to take this piece of code and want to turn it into a channel interface? Well, then I just define the predefined prompts, copy, paste, and I now have a piece of code. What if I ran this just like I did, and what if I want to optimize it for something? Here's a prompt. It's just, instead of me typing, I just have predefined prompts. Here's a prompt providing a recommendation on what we can do to optimize area. It comes out with some, you can do different types. It's a story for another section. Loop unrolling, I can ask, how on earth do I do loop unrolling? It will figure out what the code is doing. I can copy, I can paste, and now I'm good to go. Let's say that while I had this, I want to add something. So I could say, well, I like to have an input. I would like to have a SystemVerilog channel. And now the code will then try to predict what is it you may want to have next. I might want to have a BIOS. Let's see, BIOS and buff-in. We could also do buff-in. We don't want that. And as soon as I do it, I can start to continue my discussion. It will know that there's an integer. It knows that I probably want to read that from the machinery, and so it goes. You can see how typing becomes easier, especially for somebody like me. You could use the exact same mechanism to select a piece of code, generate test benches. I find that helpful. We're a startup and we're building test cases all the time when we build tests. There was a point in my life where I was typing test. Now I prompt text and I get text with instantiations, types. All I need to do is to run it. I can also build UVM skeleton structures for the same thing. I should say at this point in time, I'm running on my local machine GPU. You can get very fancy language models and you can make it even more verbose. We could also start to use documentation and create all the results as dictionaries, and you can create markdown documents that you can use for your own documentation. So for example, we could do something like this. MD, save that. What? And I will have a beautiful document based on what I ran and with some statistics, if that's helpful. I could also use the advisor generate code. So here I just have a predefined prompt, generate a CS16 algorithm, on time, channels, data types, and a UVM skeleton. I need to populate it with what I wanted to do. But I could also save myself a tremendous amount of time and just start it with the original prompt on what is it really I would like to show in the first place, which is truly about create an IP and get it going. And as soon as it's done, I can shoot it and I will end up with the example that I started with. You get the idea. Lots of saving. If you have the prompt, you can generate IPs in short order. I know we're running late, but I would love to show you a couple of examples if you offer it. If you need to run, thank you for joining. Keep in touch. Hopefully we can talk later. Here's an example that we use a lot for the exact same principles that is very easy to explain what it does. Mike talked about the test-bench infrastructures. I have a simple driver and response. I also have a much more verbose UVM structure that does the same thing. I have channel interfaces. I instantiate my dot. I have a very simple script that is running this as I'm unrolling this loop. And what I can do is just run it. You will see speed and you will see the result. As soon as we run something, we create all these parallel log files and start verification. Right, just like we saw before, it shows you power statistic, pipeline stages, the RTL implementation. And you will see that it takes a fraction of a second to do the RTL from a high-level design. It takes 5 seconds to do the RTL synthesis and 7 seconds to synthesize. Of course, that is not important in a normal day, but it shows up that we can do many things in parallel. At the end of the day, we get a table with keys, and these keys are helpful in a short moment. Keys on the different variations of the same design, the exact same design. I get different run times, design times, different power consumptions, different targeting clock, etc., etc. So what I can do, similar to Mike, just start the GUI and show you. Well, I'm challenging real estate here. Just a second. You don't see that. Let me. Maybe this can help. I can see the different variations on the loop unrolling factor, and I can see the. How do I move this? I can see as I'm unrolling, making more instantiations of the same design, the area increases. I can see power increases. I can see computations as I go and have less and less loop rolling, but more and more unrolling. The throughput of the design becomes faster, and I see that as clock cycle goes down. So based on my objective, I can see different things. Pretty cool. But what if you want to see a whole lot more? What if you really want to search the space for a design? So there we have this notion of studies. So a study is, instead of us doing the sweeping, what happens if I have this parameter, this parameters? We are defining what is it you want. I would like to have my clock to be like less than 1,000. I like to have this pipeline stages. This is my tolerance for area. And these are the parameters I like to go and manipulate the designs. And as you can imagine, there can be many. The machinery will then go and search for what might be the study set up, what might be the switches that is being communicated to the tool chain. And this is then getting executed. So I could do run me a trial. A trial is just a run. As you've seen, it happens pretty quickly, and I now get a result. And that's nice, but really what I want to do is to see the result of this trial as a Pareto fund and do general analysis. As you can see, I need a bigger monitor. But I can now run different trials, and I can stop early. And what that helps me see is, for this simplistic view, so now we just ran 11 smart settings, but we stopped early. Some of them are on the Paleo front, and here's my configuration based on my goals that I've set. So instead of going and running all by one, I can take it intelligently, and I can then do endless statistics on what is it we'd like to see in terms of best values, the different implementations, the sizing and patterns. But what if you want to do something a little bit more intelligent, where we are connecting the back end to the front end? And guess what? We have a prompt for that. Here we have a prompt similar to the other one, and these can be edited by you. It's just text, right? Just text, where we are communicating with a language model that is aware of our design, that is aware of how to run it. I have a little bit more ambitious goals. I have goals for the high-level side, the RTL side, and the same input search space. I'm enabling verification, I'm enabling implementation. And just like in TV chefs, I can open a predefined run, because the implementation takes a couple of minutes to run, and I know we don't have that. But here's a predefined run, and I can see the Paleo front. And hopefully, Paleo front, where I can see power or compute. So this is one of the fronts where all the different combinations of designs, if I wanted one that fits in my goals, I put the clock for 1100 and unroll factor for 2, or select this one. Just makes it easier for us to run the design. You see where this can go. And you can do endless analysis on inputs and output traces and see what it is. But we take that next time when we look into design. I like to spend a couple of minutes, really just a couple of minutes, showing a more realistic design. And Mike, feel free to tip in and ask questions and compliment. But this is an example that started out, it's live at Harvard University, and we're very grateful for their sharing. So thank you, Professor Lee, and now Professor Temple at Stanford University, for sharing this with us. This example is a systolic PE and a MAG and a magic multiplier. And it has a SystemVerilog MatSlick components. It has a proper test bench. It has proper design. All the principles that Mike just talked about, we see that in this example. Test bench is there. You can outline the test bench. You can see the structure of the test bench. There's a driver, there's a monitor, there's top. It has a runner script that goes through and execute all of this. So the PE arrays are getting executed by itself. The crossbar is executed by itself. But let me just run it and get you a notion of what can the throughput of a modern tool that has been architected from scratch for speed and flexibility in mind. This is how it looks like. It's running live. There's no cheating. What it does, it runs simulation, implementation, power analysis, for 3 different variations of sizes of the PE arrays. The reason why it sits here is simply just that the 16 by 16 PE array is sizable and takes some time to simulate. Once it's done, we will have, just like before, tables we can go and analyze and look at. We can navigate the design. Now let it just continue and finish up. In a second now. Tables are being created with power, with the right keys we can use for our goals. Now we have a complete set of designs. And just like before, we can go and open the design variations. We can see the 3 different permutations. We can see area for each of them, just like we're used to. We can navigate the design, take a look at how things might be looking, navigate tables, synthesis results, just like what Mike showed you. Obviously, we could talk about this for a long time. We don't have more time, but what we will do is monthly schedule and similar with different themes. We're very open for themes. Ellie will talk about what we plan to do, but please let us know if there's something you like to see in depth and we can dig into it. But for the next 4 months or so, we certainly have topics. So back to you, Ellie.
Thank you, Alan.
Thank you. And sorry for running late.
Yeah, no worries. I've kind of been texting folks a little bit, but we will finish up. So let me go ahead and share this and turn my video back on. Where did that go? Here we go. Okay, so thank you guys. I know we're running a little bit over. I'll do a quick summary and tell you about what's coming next, and then we'll open it up, see what questions. Looks like a lot of the stuff has been answered interactively already. So
yeah, I think there's an AI one that we want to give to Alan when you're done.
Ooh, that sounds fun.
Yay. So yeah, Alan, go ahead and take a look, see through some of those now. So really just kind of in summary, I know this is our first one. We crammed a lot of stuff into this 1 hour. And again, I will make sure that I'll follow up with the recording if you guys want to go back and look at other things. We deliver really a true mixed language and mixed abstraction synthesis. And this is one of the things we see as being able to really bridge this gap and provide something that's for easier adoption and for less risky adoption, and to be able to do what you need to do, because not always is different languages and for different comfort and for different purpose, right? So we allow that mix. We also have unique solutions, as you've seen the beginning of today, and I'll tell you, we're going to show you some more for both the generative AI and design exploration to help ease the adoption again, and get to give you superior design solutions with these complex designs. And then verification as a first-class citizen. We just began to hint at that, and that kind of leads me into my next slide, which talks about what we're going to do. We wanted to try to divide this up into 1 hour consumable chunks, or 1 hour and 10-minute consumable chunks. We're going to do another one where we're going to try to do it repeat this one at a little bit different time zones, so we can make our friends in India and Europe make it a little bit more convenient for them if they want to be able to not be up in the middle of the night. Then we're going to go straight into generative AI for high-level design. So take what Alan did and expand on that quite a bit, show you a lot more how it works, how you could deploy, etc. High-level verification, again, Mike just touched on this a little bit. We have a lot more on verification we need to do. System and subsystem integration, we didn't touch on that hardly at all, how it is that you can do all of this integrated into bigger system and analysis, and then look at place and route integration. So again, a whole series. Stay tuned. I will be emailing, you'll see all these in LinkedIn, or if you follow us on LinkedIn, or I will also be sending emails. So for that, I want to thank you for attending, and